Hello and welcome to this video. In this video we're going to talk about capacitors. So in the previous video we've looked at started looking at uniform fields, and we said that a uniform field is where we can have two parallel plates where one of them has a higher potential than the other, or one of them is charged positively and the other one is negative, or something like this, and it would produce a uniform field between the two plates. And we briefly mentioned that one example of a use of a uniform field would be a capacitor. Now, a capacitor is just another electrical component. So a capacitor is an electrical component, and its whole purpose is to store charge. Okay, used to store charge. So we're saying we want to put this in, and it's basically acting as almost like a portable battery, right? We want to put it onto a circuit so that we can charge or store the charge on the plates, so on each side of these plates, and then we'll be able to switch it, and then that charge will be able to flow, so it acts as a battery that you can take away from the power supply. And capacitors have the symbol like this. So it's similar to the symbol of a battery, where a battery is something like this, where one of them is big and one of them is small, but capacitors, they're both the same size because they're both parallel plates. So we have this capacitor, and then just as if we had a resistor, we would define its resistance, we have a capacitor, we can define its capacitance. Now, the capacitance is just a measure of how much charge can we actually store on these plates. So different capacitors will have different storage of plates, and we'll look at the way we can change how much charge is stored in a separate video. But the capacitance is defined as C is equal to Q over V. Okay, so this is the equation in your formula sheet that defines capacitance. And this means that capacitance is the charge stored per unit voltage. Or you could probably just simplify this. Instead of per unit voltage, you could say it's the charge stored per volt. Okay, so we may say that this capacitor has a capacitance of 10 farads. Okay, so this unit of farads is coming up again. We saw farads when we were looking at the permittivity of free space. So epsilon naught is measured in farads per meter, and capacitance is the measure of farads. So it's the charge stored per unit volt, which means that the bigger the capacitance, the more charge we can store for the same potential difference. Okay. Now, these kind of things get mathematically quite complicated, but we can relate some of the simpler things back to what we've done before. We can say, what happens if I'm in a circuit and I put in a bunch of capacitors in series with each other? How does that affect the total capacitance of the circuit? The same way that we would be concerned about adding a bunch of resistors. How would that affect the total resistance? We can say, if we add a bunch of capacitors, how's that going to affect the total capacitance? So we need to look at capacitors in series and in parallel. So we'll first look at them in series. And so if I had a bunch of capacitors, and I'm going to put ... so this could be in very, very long line. Let's call this C1. This has capacitance C1. This is C2. And let's call this Cn minus 1. And this is Cn. So I have n capacitors here, right? And in here is a gap where there'd just be a bunch more capacitors. And then they might ask, what's the total capacitance? And C total is going to be added in the similar way to we add resistors in parallel. So if I have just one here, it means that this one capacitor can store all of the charge that is in that circuit. Now, if I'm splitting all of that charge over this whole n amount of things, and n could tend off to be billions or trillions, it means that actually I'm still storing the charge, but my potential across them all is going to sum. So I'm going to end up with a much lower capacitance overall. So I actually add these as the reciprocals. So 1 over C total is 1 over C1 plus 1 over C2 plus all the things in between up to plus 1 over Cn plus minus 1 plus 1 over Cn. So I add them in the same way that I would add resistors in parallel. So this will be the opposite of resistors. So let me just write that here. So it's the opposite of resistors. And this is the way that I remember it. The way to remember it, just remember that they follow the opposite trends resistors. Now, I haven't put a box around this formula because this formula is not in your formula sheet. It is just something that you have to know, but it's very rare that they actually test you on this knowledge, but it is also, obviously, just in case it comes up, it's worth noting. So then we need to say, what about if we put capacitors in parallel to each other? And we've already noticed that we have an opposite trend to resistors. So that means that if I have capacitors in parallel, I'm going to end up with a capacitor here and another capacitor here. And I'm just going to do 3 for this case to simplify it down a little bit. And I will add these the same way I add resistors that are in series. So I say, let's call this C1, this is C2, and this is C3. C total is C1 plus C2 plus C3. So I would just sum up their capacitors or capacitances. And that's just because each of these things will have the same voltage, and if they store the same charge or they store different charges, I'm just going to sum the amount of charge that I'm holding on each of them divided by the same amount of voltage, so I can just have a linear sum of these things. Okay, so capacitors will work by charging them up first so that they gain all of the charge and then discharging them afterwards. Now we're going to do a separate video looking at charging and discharging because this is where things get a little bit mathematical. But for now, what we should take away from this video is a general idea that capacitors are just an electrical component that we can put into a circuit in order to store charge, and then we can use that capacitor with fully charged to then discharge it over a different component or different circuit entirely. We can say that we can define capacitance by the charge stored per volt, and we say that when we add multiple capacitors either in series or in parallel, it's just the opposite trend to how we add resistors. Thank you for watching.